Okay, got it. Ready.
Hello everyone. Hope you had a good sleep before reviewing this project today. Just kidding. This is Team K4. I'm Vijay Gopal Sami.
I'm Dawood Mahmood.
Welcome to our presentation on reproducing the research WatchSleepNet for sleep stage classification. The research paper has published a novel algorithm that can be used through risk-based sensors to accurately measure the quality of sleep. So the problem statement, why is it important to study the sleep quality? In today's busy world, we see increase in people with sleep apnea, insomnia, and other sleep disorders. The tools we currently rely on to study have important limitations. On one side, we have clinical sleep measurements. On the other side, we have consumer wearables like smartwatches, Ring, and fitness tracker. These are convenient and widely accessible, but they struggle with accuracy. The clinical measurement, although it's available, it's very expensive, requires full night sleep in the lab, and the environment is artificial, meaning patients don't sleep the way they normally would do. So the challenge is clear. Clinical measurements are accurate but impractical for everyday use, while consumer wearables are practical but not yet reliable enough for clinical adoption. Our goal is to close the gap between clinical sleep measurement and wristwatch based tracking. While polysomnography offers rich, validated data for diagnosis, it's costly and impractical for long term use. So here's the approach we followed for reproducibility study. Define the reproducible scope, dataset collection and pre-processing, research execution, which included machine learning coding, training and evaluation, results comparison, and the conclusion. The scope, to evaluate the claim, we structured our study around three core hypotheses. The main one is WatchSleepNet can learn sleep stage patterns from wrist accelerometer and heart rate data. The second, temporal modeling hypothesis, that components like TCN and bidirectional LSTM are essential for capturing sleep stage transition and temporal dependencies. And the third, the attention mechanism hypothesis, that multi-head attention improves performance by focusing on relevant temporal windows within long input sequences. So what's our high-level execution flow? Let's look at the high-level execution flow. We began with the original data set of 100 participants and used it as used in the original research. Due to computational data constraint challenges, we selected a subset of 9. Each participant data in the CSV file has 1 million plus records each participant containing wrist-based accelerometer and heart rate signals. We compiled all findings into a final report after running it through the machine learning algorithms, summarizing our results, comparison with the original paper, and insights into reproducibility under constrained conditions. Um, there are libraries that we used like PyTorch, scikit-learn, NumPy, TensorBoard, Matplotlib, and Seaborn. To discuss further into implementation and evaluation in detail, I will hand it over to Dawood. Dawood, here you go.
Thanks, Vijay. So yeah, let's talk up implementation. So we implemented the WatchSleepNet with about 2.1 million parameters in PyTorch with four components that Vijay just mentioned, the feature extractor, TCN, LSTM, and the attention. Our key challenges were synchronizing the multi-rate signals, so the 32 hertz accelerometer, the 1 hertz heart rate, and our 30-second labels, plus handling the severe class imbalance. Was another challenge that we had. So we used weighted loss to prevent NREM-only predictions. And then we used Claude AI to help with boilerplate and debugging, saving us about 15 to 20 hours of development time. So next, let's move on to our evaluation approach. For evaluation, we used patient-level splits, 5 for training, 1 for validation, and 3 for testing. So the patient-level splitting prevents data leakage. The model must generalize to see any unseen individuals. And then we used Cohen's kappa alongside accuracy, where kappa accounts for the chance agreement. A model always predicting NREM would be getting 68% of accuracy, but really zero value. So our kappa of 0.216 shows genuine learning beyond just chance. Next. So our baseline model training dynamics. So this shows our training over the 16 epochs. Training loss decreases steadily while validation fluctuates due to our single patient validation set. So our best validation loss was at epoch 6, but we selected the epoch 10 for final evaluation because it achieved a 67.24 test accuracy. And then our early stopping triggered at epoch 16 because nothing had changed or improved for 10 epochs. And next we'll go over our results. So our results were 67.24% of test accuracy with a kappa of 0.216, which was double random chance. So our NREM actually achieved a very strong F1 at 79.44%. So this model excels with many examples. Our wake got about 50.83% F1, which is pretty moderate, but our REM was challenging. That one only got 10.33% F1. And the confusion matrix on the right shows 79.1% of REM was misclassified as NREM. This reveals a fundamental challenge. REM involves muscle atonia, which is temporary paralysis, which looks identical to NREM from a wrist accelerometer. Plus, REM is rare. Just 15% of our data was REM. So rare examples plus ambiguous signals means that this model really struggles to identify REM sleep. Next slide. So our comparison of our test to the original paper. So they used 100 plus patients for multiple data sets, achieving 80% accuracy, whereas we used 9 patients with 67.24% accuracy. So our key finding was that we achieved 84% of their original performance with less than 10% of the data, which validated that the architecture is is sample efficient. Our NREM F1 was pretty close to theirs, but REM F1 was 10.33%, which was far below their 60%. Why? The dataset size. So they had 1,500 to 2,000 REM windows, whereas we only had 110. The second one would be diversity. They combined multiple sources, whereas we only had one data set. And lastly, REM varies between individuals, so it requires significantly more patients than we had. So the 84% retention proves robustness despite the limitations.
Yep.
And then our next slide, we're going to go into some ablation studies. So we want to look for comparing TCN versus attention. So we tested ablations to understand component contributions. So we tried with TCN only, and this one achieved the highest accuracy at 73.29%, but poor class performance. The next one was our attention only, which had the lowest accuracy, but best REM detection at 20.46% F1, triple the TCN alone. The best was the full model, which balanced both because it gave us the best kappa at 0.216. So our key finding was that TCN captures temporal patterns, attention balances the classes, but both are necessary for balanced performance. And next, we're going to talk about the key takeaways. So we validated the architecture. Our WatchSleepNet is reproducible with limited data, 67.24% accuracy. What worked was robust pre-processing, class weighting, and patient-level splits, and AI assistance, saving us about 15 to 20 hours. The ablations show that TCN and attention are complementary to each other, but kappa matters for imbalanced medical data like we have here. Our limitations were, as we mentioned, 9 patients impacted REM performance. The gap from 60% to 10% F1 shows the rare classes needed scale. But for future work, we would do some transfer learning, multimodal fusion with temperature and EDA, and larger studies. But in conclusion, WatchSleepNet is sound, reproducible, and shows promise for accessible clinical sleep monitoring. Thank you.
Thank you.
I think we did it.
Did you stop it?
Yeah, the recording's still going. We can